So first off, we have what happens to the vertical velocity of an object as it goes up. So an object that is thrown into the air, let's say straight up, is traveling against gravity. So I'm going to show gravity as a green arrow downward towards the ground. So this downward arrow shows the force of gravity. The upward arrow shows the path or the velocity, the initial upward velocity. Now, when this ball is traveling, or whatever it is traveling against gravity, it's slowing down. So anytime you're going in the opposite direction of the force applied, which is causing that acceleration, it's actually going to decrease in speed because these are oppositely acting factors. The ball is moving upward, but the force is pulling it downward, which is kind of like the dog on the leash. So the dog's running away from you, you pull the leash towards yourself and you slow the dog down. So in vertical motion, what happens is the object keeps moving upward until it stops, and then it comes back down. So because that force that caused it to slow down is still acting on it and is pulling it towards the earth. So it's going slower, zero. And then once it gets to zero, it can't just hang there. There's nothing holding on to it. So it falls back down, all the way back down, speeding up as it goes down. So question 1, what happens to the vertical velocity of an object that goes up? Well, it decreases. Next question, number 2, asks us what happens to the velocity as it comes back down. And I've explained it up here with the same drawing. So when it's on its way down, it's speeding up. It's the same thing. So if I take an object and I throw it up and then I catch it, it goes up to 0, comes back down. Or if I simply just drop it, it's the same motion because it has to stop. So you have to stop going up to start going down. And so it's starting from 0 and it's speeding up as it falls. So what is happening when it comes back down? It is increasing. What happens to the horizontal velocity as the object goes up? Now, horizontal velocity we've described as being constant motion. So if I were to take a picture of an object and I took each picture in equal intervals of time and then I overlaid those pictures and I saw a pattern like this, what this would tell me is that for every time interval in between when I snapped the picture, the object moved an equal distance. Okay, so let's say that this distance is 1 meter and it was 1 second. So that means in this time, this second, it also traveled 1 meter in 1 second, and so on. So this illustrates constant motion. Constant motion is motion that is not accelerated, meaning it's not speeding up and it's not slowing down. So what happens to horizontal velocity as the object goes up? Well, they're not related. The up and down motion is based on the vertical velocity and gravity, which is pulling it down. Horizontally, there are no forces applied. So up and down, there's gravity always acting down, which is why it goes up and then down. But in the horizontal direction, there's no force opposing or pushing it forward. It doesn't have wings. It's not a rocket. There's nothing pushing or pulling it. So it remains constant. This is once going back to Newton's first law of motion. An object in motion will remain in motion in a straight line unless acted upon by a force. So an unbalanced force. So this illustrates that exact situation. So what happens to the velocity as it goes up? Well, it remains the same. Okay, number 4. Which time would be used to determine the maximum height? So again, we have our upward motion going up to 0, and then we have our downward motion. Now, the acceleration due to gravity is 10 meters per second per second. This means that it changes the velocity by 10 meters per second every second. So if I start out at, let's say, 30 meters per second upward, okay, then gravity will change it by 10 every second. So 20, 10, and then 0. Now, these are not equally spaced. It travels much further in the first second because it's going 30. And then by the time it's traveling only 10, it's going a much shorter distance, but I don't really have the ability to scale this very well. So just use your imagination. So because 10 is acting down, that would be a negative 10. And this, in this part of it, it's going up. So we would be a positive number. So minus 10. So each second, so this would be 1 second, 2 seconds, 3 seconds. It would be going up for 3 seconds if it started at 30 meters per second. Once we get to 0 up here, gravity is still acting on it, but now we're going to be going down. So we're going in the negative direction now. So after 1 second, we would be going minus 10 because gravity is negative 10 meters per second squared, which means that every second we're going to change by negative 10. So then after 1 more second, we'll be going negative 20. 1 more second, we'll be going negative 30. And that's the speed we'll be going when we get back to the ground. So which time is used to determine maximum height? Well, it takes the same 3 seconds to go up as it does to come down. So either one would work. Either time up or time down would be the appropriate amount of time to know how high up it went. In 3 seconds, we would know 10, 30, 20, 10, 0 are the velocities, and then we could do a calculation. Now, we don't do kinematic equations in this class very often, so we never really did these types of calculations, but you can calculate it with a formula and identifying your variables. We're more concerned about, do we understand what's happening here? We have an initial velocity going upward. It decreases by 10 every second because of gravity. Once it gets to 0, it has to come back down, and then it increases by negative 10 every second until we get to the ground. Question number 5. Which time is used to determine the x displacement? Now, remember the drawing with the dots. Okay, try to get these. That's not very even, but you get the idea. And then every time interval, there was an equal distance traveled and so on. So the object travels from left to right in this picture the entire time it's in the air, from when it leaves the ground to when it reaches the ground. When it goes from the down to all the way back, it goes up and then all the way back down. The time in the air is based on how long it takes it to get up here and then back down again, right? So during this entire time while the ball is going up and then coming down, the ball is traveling to the right. And it's traveling at a constant speed because there are no forces acting on the object in the horizontal direction, which means that we need to know how long the ball is in the air total to tell how far it went. So if it was traveling 1 meter per second every second, that was our velocity, meter per second in this direction, and we were in the air for 6 seconds, that would mean 1, 2, 3, 4, 5, 6 meters is how far we went. So to determine that x displacement of 6 meters, we needed to know how long the ball was in the air altogether. So we need to know the total time. Number 6, at what point in the pathway is the vertical velocity equal to 0? I've drawn this a couple of times already. Going upward, we go from some number, let's say 30, all the way to 0, and then back down, 30 again the other way. So when is the vertical velocity equal to 0? Right here at the top, we would call that the peak. So this would be the start, this would be the end, and then of course never is self-explanatory. So when is the vertical velocity 0? At the top there. Number 7, at what point in the pathway is the horizontal velocity equal to 0? So this comes down to just remembering this concept that horizontal velocity is constant. It's a constant motion. It travels the same amount of distance every time interval. So it's not speeding up or slowing down, so it would not be 0. Now, the only time horizontal velocity can be 0 in a projectile is if it goes straight up. So if all the velocity is upward and none of it is to the side, then that is when horizontal velocity would be 0. But in this picture, there has to be a horizontal velocity. That's the only reason it's traveling left to right. So never in this particular case. Number 8. If an object is launched at the angles below with the same initial velocity, which ones will land the furthest away? So all right, so we have our baseline, and then we have our vertical axis, and then we have a 45-degree angle. Okay, so this is 45. And 45 lands the furthest away. Now, that's not a choice here. We have 25, 65, 40, and 70. So the other thing you need to know, the other rule you need to know about figuring out which one it is that this property of projectile motion. So at 45 degrees, we get the furthest distance, okay? But as we increase or decrease our angle from 45, so either less of an angle or more of an angle, it doesn't go as far. It doesn't go as far to the right. Okay. And so it actually is extremely mathematical. So if this is 45 and this is 25, okay, so that's 20 less. 45 is 20 less than, 25 is 20 less than 45. If I then go 20 more than 45, so 65, those two angles will land in the same place. Both 25 and 65 are 20 more and less than 45 and will land at the exact same place. So as I get further from 45, I get closer and closer and closer, which eventually, if I go straight up and straight down, that's the least far, right? That's like no distance. So of my choices, I have 25, 65, 40, and 70. 25 degrees is 20 less than 45. 65 is 20 more than 45. 40 is 5 less than 45. And 70 is 25 more than 45. So the correct answer would be 40 degrees. That's the closest to 45 and would therefore travel the furthest. Question number 9. Which other angle would land at the same spot as a 35-degree angle? So as we just discussed, 45 is the furthest. So to determine equal angles, we have to go above and below 45. So 35 is 10 less than 45. So this is 10. So then we need to go 10 more than 45 to get a matching angle. So 55. Correct answer, 55. Last question, number 10. Which angle below would keep the cannonball in the air for the longest period of time? Assume all start with the same initial angled velocity. The amount of time a projectile stays in the air is determined by its initial vertical velocity. So how much velocity it has going upward. Because the upward motion is decreased by 10 meters per second every second because of gravity. So if we start at 30, we might go this high. If we start at 40, we might go this high. If we start at 20, we may only go that far. So the faster we're going vertically, the longer we are in the air. Looking at the pictures here, we can see that if we draw an arrow from the baseline to the top of the peak of each curve, it shows that at 60 degrees, it travels the highest, which means it was traveling the fastest in the vertical direction initially, and it takes longer for it to stop. Okay, so all of these increase until they decrease their velocity till they get to 0, and then they come back down. So because this one is higher, it means it was in the air longer. If it went further, it was in the air longer. And therefore, which one would be in the air for the longest period of time? That would be 60 degrees. It was in the air the longest because it traveled the highest. Now, this is the result of the fact that velocity at an angle is actually a vector quantity. This is a concept we didn't cover very much, but basically every motion in this case has a vertical amount and it has a horizontal amount. And if you have a lot of horizontal amount and a little of vertical amount, you'll have a low velocity vector. If you have a large vertical component and a small horizontal component, you will have a combined vector more upward. So the starting angle here illustrates that for 60 degrees, there's a larger component upward than there is to the right, which results in this larger vertical velocity and therefore larger height.